Hello everyone. Today I'm reviewing a compact yet very powerful DC-DC converter. This DC-DC converter uses a SEPIC topology. This means it can step up as well as step down the input voltage. The device is called the XY-SK120. Here are its main specifications. The maximum output power is 120 watts, but it can be increased to 150 watts. The output voltage can be adjusted from 0 to 36.5 volts. The output current is up to 6.2 amps, but can be limited to 10 milliamps. The converter's supply voltage ranges from 5.5 to 36 volts. The module is also equipped with a charge meter. It displays the energy transferred to the load in ampere hours. Therefore, when charging batteries with this device, you can easily check their capacity. There are also several protections: low and high voltage protection at the input, overheat protection, output short circuit protection, and a number of other protections, which I'll discuss later. If you purchase a Wi-Fi module, the converter can be controlled either from a computer or a phone. And if you connect a CAN bus adapter, you can control not just one, but several of these converters from a computer. The front panel of the converter is very minimalist and simple. The LCD display isn't very large, but it's not small either, and it has an LED backlight. There are 4 buttons and an encoder. The encoder can be pressed as well as rotated. There are latches on both sides to securely hold the device in a housing. There are a lot of components on the back that I'll definitely cover, including a terminal block, 2 pins for input and 2 for output. The positive and negative pins, input and output, are labeled. The converter components that get very hot are located on the heatsink. A small but very high-speed fan is used to cool the heatsink. The fan wires are connected to the board using a small connector. The fan turns on when a certain load limit is exceeded or due to high temperatures. Other times the fan is off. There's a second board inside, under the external board. The external board is held in place by side connectors, which you'll see later, and one small screw in the lower right corner. Part of the terminal block is removable, which is very convenient. You can easily insert the wires into the removable half and, if desired, apply full force to tighten these small screws. This is also very useful if you need to mount this converter in a small case. The entire converter consists of 3 large parts, 2 boards, and a case. The boards are connected to each other using pin connectors. Now let's take a closer look at what's on the board. What's unusual here, of course, is that there are 2 inductors on the board. This is a characteristic of the SEPIC topology. On the left, 2 470 microfarad 50-volt capacitors are soldered parallel to the output terminals. Both have low internal resistance and can withstand temperatures up to 105 degrees Celsius. Behind them is a 2 kilo-ohm load resistor. Like the capacitors, it is soldered parallel to the output. On the right is another 470 microfarad 50-volt electrolytic capacitor and a 220 microfarad 50-volt polymer capacitor. The electrolytic capacitor is parallel to the input. However, the input power here is not supplied directly to the entire circuit, but through a field effect transistor. It acts as a switch here, and I'll talk about it a little later. Therefore, if you test this capacitor relative to the input, only the positive side will go directly, while the negative side will go through the transistor. This is the fan connector, and this is for the remote temperature sensor. The Wi-Fi module is connected to the third connector. The chip is a step-down DC-DC converter XL-1509. Its input can accept up to 40 volts, and the output is a fixed 5 volts. This chip controls the entire device and also powers the fan. Next to it is a 50-volt, 4.7 microfarad capacitor. The single heatsink houses a field effect transistor and an array of dual Schottky diodes. The diodes are B20100G, rated at 20 amps and 100 volts, but the transistor could not be identified. The field effect transistor's markings are hidden by the connector. The internet says that's what it is. The fan here is 5 volts and is attached to the heatsink with 2 screws. The heatsink, in turn, is also attached with 2 screws to the diode array and transistor. The heatsink is suspended in mid-air and is not secured to the board. However, there is a hole in the board under the heatsink, apparently intended for a screw to secure the heatsink. The diode array and transistor are attached to the heatsink via thermally conductive pads and dielectric washers. Therefore, the heatsink is not connected to any conductive parts. There are many more components on the backside. Here is a 47 microhenry inductor, a 220 microfarad 6.3 volts capacitor, and 2 diodes. One of them is an SS34. This is a 3 amp 40 volt Schottky diode. All these parts are part of the buck converter harness that powers the entire module. The other 8-legged microcircuit is, so to speak, the heart of the entire device. The SEPIC converter's topology is built around it. A schematic for this converter is available in its datasheet. You can see here that it has 2 inductors, and through a driver consisting of 2 bipolar transistors, it controls 1 high-power field effect transistor. These 2 microcircuits are the LM358 operational amplifier. Here are 2 high-power resistors soldered in parallel, each rated at 1 watt and with a resistance of only 50 milliohms. They act as a shunt, measuring the voltage drop across them. This is how short circuit protection and current stabilization work. Here is a small 2.2 microhenry inductor. This is a 5 amp 40 volt Schottky diode. It's parallel to the converter output, but connected in the opposite direction. It's the basis for protection against incorrect connection of the charging battery. Suppose I mess up and connect the converter's positive terminal to the battery's negative terminal, and the converter's negative terminal to the battery's positive terminal. A short circuit will occur across this diode. However, this protection will only work with weak batteries. If the battery is powerful, this diode will simply burn out, and then the entire converter circuit will burn out. This is a 70 volt, 56 amp field effect transistor. Its junction resistance is only 10 milliohms. I mentioned it a little earlier. It's located at the converter's power input. It's controlled by a microcontroller and can turn the entire module on and off. This small component resembles a thermistor. Perhaps this is where the module's temperature is measured. This is a diode with the code marking MP. This is a so-called TVS diode or suppressor. It's placed parallel to the input after this field effect transistor. It protects against high input voltage. If the input voltage exceeds 40 volts, the diode will break down and cause a short circuit. It's also assumed that the power supply that powers this converter will go into protection mode. Either burn out or blow a fuse if you have one. But this diode is also weak and will evaporate under the influence of a powerful power supply. In general, it can be assumed that if you reverse the polarity at either the input or output, no protection will help, and the converter will most likely burn out. So you need to be very careful with this. Although the negative terminals are located next to each other on the terminal block, they are not connected to each other in any way, so I don't recommend shorting them. In addition, manufacturers often recommend keeping the output wires away from the input wires in such converters. Short-circuiting them can also damage the device. The second board on the front side contains 4 buttons, an encoder, and an LCD display. The display is pressed to the board by a plastic frame secured with 4 screws. Under the display is a light diffuser, and on the board are 3 LEDs for backlighting. The other side looks like this. The largest microcircuit is the LCD display controller. This microcircuit is another microcontroller. It controls the operation of the entire module and houses the operating system. It houses a 64 MHz processor based on the ARM Cortex-M0 core and 64 kilobytes of flash memory. The board also contains an LM321 operational amplifier, a buzzer, and several small transistors. I didn't buy a remote temperature sensor or a Bluetooth module, but I'll be using my own temperature sensor for testing. This is a 10 kiloohm NTC thermistor. The top left button is called VSET. It's called that because it allows you to change the voltage parameters. That's its primary function, but it also performs a number of other minor functions. Below is the SW button. I assume it stands for switch, which also has several functions. And below that is the I-set button. Its primary function is setting the current. Beyond that, it also has many minor functions. On the right is the encoder, which adjusts the current, voltage, and changes some parameters. Below that is the button that turns the converter output on and off. When I apply power, the module turns on and beeps. This is the converter's main screen. During operation, you'll mostly see it. The display shows 3 lines of numbers. The first displays voltage, the second displays current, and several parameters are displayed below, such as output power, set voltage, set current, amp hours, and temperature. Currently, the temperature of the remote temperature sensor is displayed here. However, if it is disconnected, the inverter temperature will be displayed. An icon labeled CV is displayed here. This indicates that the inverter is in constant voltage mode. The OFF icon is lit here, indicating that the output is currently disabled. And below, the labels SET, CV, and CC flicker on and off. They indicate the current voltage and current settings. Now the temperature sensor shows the room temperature. I'll touch it and see if the temperature rises. Yes, the temperature sensor is working. The temperature is rising. To open the converter output, press this button. The ON icon will light. After that, the first line will display voltage, and the second line will display current. Currently, I'm using a small fan like this as a load. If I press the output activation button again, the fan stops and the current stops flowing to it. I press the button again to open the output, and the fan starts again. It's pretty simple. The voltage is adjusted by turning the encoder. The voltage can be adjusted both when the output is off and when it's on. The minimum voltage adjustment increment is hundredths of a volt. If I want to move the cursor further, I need to press the encoder. Thus, each digit of this number can be changed separately. But the tens digit cannot be changed, only the ones, tenths, and hundredths. In addition to pressing the encoder, you can also use the SW button to scroll through the digits. This is much more convenient and faster. To exit the voltage adjustment settings, you can press VSET. After this, the third line will display various parameters in demo mode again. If you press the encoder, you can scroll through these parameters manually. If you stop scrolling, these parameters return to demo mode. The output is currently closed, but if you open it, you can view the parameters in the same way by pressing the encoder button. But there is a slight difference. If the output is open and I scroll through some parameters and stop at 1, it will remain displayed on the screen. Let's say the ampere hours are currently displayed here. This makes it easy to monitor the battery's capacity. If I close the output again, the parameters will return to demo mode and be displayed one after another. If I press the SW button, the first line will display the input voltage instead of the output voltage, and the IN icon will appear here. This is the voltage of the power supply that is currently powering the entire module. If the power supply is weak, you can immediately see how much the voltage is dropping. At this time, you can also turn the output on and off. Pressing the iSet button will take you to the current settings menu. Pressing the encoder here also allows you to navigate through the digits. Turning the encoder increases or decreases the digits. To exit the current settings, press iSet again. If you hold down the VSet button, you'll enter the memory cell selection menu. These can also be called presets. There are 10 of them here. They're simply named CD0 through CD9, and each one can have its own parameters, voltage, current, and various protections. But in this particular menu, I can only change the voltage and current. This is like a quick way to change memory cells. The VSet button moves forward line by line, and the iSet button moves backward. As before, pressing the SW button moves through the digits. You can rotate the encoder to move through the memory cells. Each memory cell can be customized for different purposes. Let's say one is for charging lithium-ion batteries, another for charging a phone, and a third for charging lead-acid batteries. Or you can dedicate cells to higher voltages, for batteries with 5 or 10 cells. To exit the memory cell selection menu, you can long press VSet or simply press the encoder. After that, the settings for the selected cell will appear on the main screen. Selecting memory cells is very simple and greatly speeds up work. If I long press the SW button, I'll enter the Interface and Display Settings menu. On the first page of this menu, called BEP, short for beeper, you can turn the beep on and off. If off is displayed, it's disabled. If on is displayed, the beep is on. You can change this by turning the encoder. I click VSET and move to another page. Here you can adjust the display backlight brightness. BL is short for brightness level. It's adjusted with the encoder from 1 to 5. On the next page, you can select the temperature unit, either Celsius or Fahrenheit. On the next page, you can configure what will be adjusted with the encoder on the main screen. Currently, the voltage is adjusted. You can also set the current adjustment. And here you can also set the constant power parameter if it's enabled in other options. Or set it to off to prevent accidentally increasing the voltage when turning the encoder. On the next page, you can set the device address or the serial number of this module. This is necessary if you have multiple modules connected to the computer and each has its own load. On the next page, you can change the data transfer rate. There are 9 speeds, so to speak. Each number has its own speed associated with it. This configures the solar panel operation mode using the MPPT protocol. You can set it to either on or off. Clicking SW or the encoder will change this coefficient. I don't know how this function works. If you know, please let me know in the comments. This configures the constant power setting. If I activate it, I'll be able to adjust the power in the main menu instead of adjusting the current. This configures the battery charging start voltage. When the battery voltage drops to the set value, charging current will begin to flow. If you press the output open button, the dashes will change to numbers, allowing you to enter the desired voltage. Note that a battery icon has appeared on this page. The next page also displays battery charging parameters, but they are related to current rather than time. To activate this parameter, press the output button. At the very beginning of charging, the current is always high. But as the battery charges, the current will drop. Here you can set the current at which charging stops. Voltage calibration is configured here, and current calibration is on the next page. This is necessary in case the device displays current or voltage incorrectly. But if you don't have a reference voltmeter or ammeter and the device displays everything correctly, it's best not to bother here. On the next page, current calibration is configured, but this time for 0. If for some reason the device displays a certain current at the output without a load, you can reset it here. Here you can configure the parameter for disabling the output when changing memory cells. Imagine that the converter output is open and a load is connected to it. The load is very important and expensive. Let's say it's a phone and you're charging it with 5 volts. Then you select another cell, and it's 20 volts. In this case, to prevent the load from burning out, the output will be turned off when the memory cell is changed. If this setting is on, the output will be turned off when the cell is changed. But if it's off, it won't. Then the voltage with the new parameters will immediately be applied to the load. On the next page, called Power Off, you can enable the converter shutdown parameter. This is done by holding down the output open button for a few seconds. If it's off, the device can't be turned off. But if it's on, it can. The next page performs a factory reset. To do this, hold down the output open button for a few seconds. The last page simply displays the software version. After this, all the pages will scroll in a circle. To exit these settings, hold down the SW button. Next, I'll show you how to configure memory cells. To access their settings, press the iSet button for a couple of seconds. A page like this will appear. You can change memory cells by rotating the encoder. When I reach the cell I want to change, press the VSET button. The device will then enter that cell and will configure all subsequent parameters only for that cell. Now the first line displays the cell name. The second line displays the name of the function we're configuring, and the third line displays its parameter values. The first page of the cell configures the voltage. To move to the next page, press the VSET button. The stabilization current is set here. The third page configures the low input voltage protection. The factory setting is 5.5 volts. You can't set it lower, but you can set it higher. The fourth page configures the output over voltage protection. The next page configures the output over current protection. The sixth page configures the output over power protection. As I mentioned at the beginning of the video, although the converter is rated for 120 watts, you can increase its power range to 150 watts. The seventh page configures the ampere-hour limit supplied to the load. If the function is not activated, there will be dashes here. To activate it, press the Output Open button. After that, numbers will appear, and you can enter the required values. Next, it's almost the same, but with a limit on the watt-hours supplied to the load. Then, the operating time limit for one work session. On the ninth page, you set the over-temperature protection. Keep in mind that this is the temperature of the converter, not the remote sensor. The remote sensor temperature protection is configured in the next country. By default, it is disabled, even if a temperature sensor is connected. To activate it, press the Output Open button. On the next page, you can enable the Output Open function after power is applied to the converter. This was the last function in the memory cell settings. From now on, everything starts over again. To exit this menu, long press SW. Now let's move on to the tests. First, I'll compare the converter's output voltage accuracy with my multimeter. This one. This multimeter will display the output current, but that'll come a little later. Now the voltage is 0 volts, and I'm starting to gradually increase it. the voltage is half a volt. The readings are roughly the same, 1 volt. The difference is insignificant. "5 volts. The difference is 0.05 volts. "10 volts. The difference is 90 millivolts. At 15 volts, the difference is 110 millivolts. "20 volts. The difference is 180 millivolts. 25 volts. You need to switch the multimeter to the 200-volt measurement mode. And here the error is also approximately 0.2 volts. At 30 volts, the error is approximately the same, but the voltage sometimes drops to 29.7. With the maximum voltage on the converter of 36.5 volts, the multimeter only shows 36.2, a difference of 300 millivolts. I've just shown the difference between a converter and a multimeter, but I won't judge exactly which one is showing the difference. The multimeter may be distorting the readings slightly, or it may be the converter. In any case, the difference is very small in my opinion. Now let's compare the output current in the same way. Behind the scenes, I have an electronic load connected. I'll use it to load the converter, and this multimeter will display the current. This multimeter will also display the voltage at the converter's output. The tests will be conducted at 5 volts. Note that under load, the voltage will drop, but this drop will be due to the long wires, while the voltage at the converter's output will remain the same. I'll demonstrate this in another test. Under load, the voltage remains stable. I begin to increase the load. The multimeter shows a current of 1 amp. The converter shows a slightly lower current. The multimeter shows 2.1 amps, and the converter shows almost the same, but still slightly lower. "3 amps. Both devices show almost the same. "4 amps. The difference is the same. Now the current is 5.1 amps. Now the maximum current is 6.1 amps. The converter has switched to current stabilization mode. At this point, the multimeter shows a slightly higher reading. As with voltage, the difference is within the error range. Now let's move on to power tests. Let's see if the voltage sags under load and how hot the converter gets. This multimeter shows the output voltage. This ammeter shows the output current. Its readings will slightly differ from the module's current. And behind the scenes is the electronic load. I'm supplying 24 volts from the power supply to the converter input. Note that the converter temperature is 41 degrees Celsius. The converter output is now 10 volts. This time, the multimeter that displays the converter voltage is connected to the converter terminals with short wires, so we can monitor whether the converter voltage sags or not. I begin to increase the load. According to the converter, the current is almost 6 amps. The voltage dropped by about 10 millivolts. That's 60 watts of power, half of what the converter can deliver. Now I'll do the same thing, but instead of 10 volts, I'll increase it to 20. Note that under load, the voltage remains the same. The converter handles the load well. A current of 5.4 amps is almost 108 watts. Under this load, I'll leave the converter for 20 minutes, and then I'll speed up the video. Watch the temperature rise, but ignore the current increasing over time. My electronic load has a temperature drift, so the current begins to change. So at 20 volts and 5.6 amps, the temperature rose to almost 80 degrees Celsius in 20 minutes. The module case has gotten quite hot. The built-in temperature sensor shows 79 degrees. The output capacitors are the hottest. They're so hot you can barely touch them. Apparently, they're heating up the board where the temperature sensor is located. But the heatsink with the diode array and transistor feels about 40 degrees. They don't get very hot. The converter passed this test successfully. The current power was 113 watts. I think the temperature will be exactly the same at 120 watts. Of course, it's unclear how it will perform in a case. Most likely you'll need to make a hole there and install a fan to suck out the air. Let's move on to the next test. Now I'll test the converter at maximum power. The output voltage is currently 25 volts, and the current is 5.5 amps. That's about 137 watts. The inverter temperature is 70 degrees. I've sped up the video here, but still, notice how quickly the temperature rises. The heat is much higher than in the previous test at 113 watts. In 7 minutes, the inverter reached 90 degrees. A little more, and it'll be good for boiling water. This is a very high temperature for electronics, so I decided to end the experiment. It turns out the converter handles its stated 120 watts well. But problems begin with higher power. But if the load isn't constant but is connected periodically, and the converter will cool down between cycles, then why not? It can also be used at this power. Another thought occurred to me. The minimum voltage at which the converter can operate is 5 volts. That's very good. But if we have a 120 watt output load, then the input power should also be the same. And considering the efficiency, it should be even higher. So, with 5 volts at the input, the current will be 24 amps. I highly doubt the terminal block and the circuit board tracks can handle that kind of current. You can, of course, power the converter with 12 volts, but then the current will also be around 10 amps, or even more. Therefore, I think it's better to supply a higher voltage of 20 volts or more to the converter input to reduce the current. This video ends here, but it doesn't end the story about this converter. The video is already very long, but I wanted to show how some of the protection devices work. so I'll have to make a second part. If anyone is interested in the device, they can purchase it by following the link in the description. That's all for today. Subscribe, like, ask questions in the comments if anything is unclear, and bye everyone.